we are going to discuss about my CWS project. That's nothing but Enigma E model. So what exactly is my C++ code and everything about its working, the for loops, this, that, everything. Before knowing that, we should know why exactly I made this. And to tell that, we will look at Enigma, what are its functionings, and to actually understand the code, it is easier if you're able to visualize it. And if I explain you the Enigma machine, it is going to be way easier. So let's begin with the description of the Enigma machine and how exactly was it working in the past. So what exactly is Enigma? So it is a bunch of guess as it is written here, like it is dependent on mechanical guess, this, that, basic circuits for encrypting and decrypting. So first of all, looking at the history, this was used during the very old time, like World War II, but why it holds significance? We are going to cover that in the coming slides. And some of its components are plug board and bulbs. So this is called as the plug board, and those wirings are called as plug board wirings. We are going to discuss this as well, and those are the bulbs. So just as we have display out here, and like when you're watching the video, you're watching it on a display. Similarly, the bulbs act as the display and give the output for the encrypted message, which is per letter. And those things which are popping out are called as the key switches. And this is something called manual plug board and rotor settings. So why exactly is it manual? It's because I can manually set all those things. And rotor settings basically means those things, something related to that. Let's not look into that for now because I'm going to tell about that later. So looking forward, we have our oldie, which is nothing but the Enigma E model. And let's rotate the gears a bit. So the basic circuit begins with the key switches. As I showed you, the key switches are nothing but those popping out buttons which we have to press, and this is an electronic device. So every time you press any button, as the output, some of the bulb will glow and show you the encrypted letter in place of that letter. So we will be also looking at the circuit in a short while, but let's see a video so that we can actually understand how actually the current is flowing from the battery and how exactly are the rotors, which are a very important part of the project, and then the plug board is working. So here comes the video. Just a second, I'll pause so that I explain you the components first. This part which you can see here is called as the battery. So that is the powerhouse basically. And here is our key switches, set of key switches where we are going to type our message, blah, 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 blah. And from here, the message goes to the plug board where I will show you in a minute. And here is the output key switches. So basically here is the battery, plug board is right here, key switches, bulbs, and those are the three rotors. You can see here the separations, right? The separations in orange. So those three comprise of the rotors. And this part out here towards the extreme left is called as the reflector. So let's see how exactly the current flows and how exactly we get the encrypted output. So here it begins. First, as soon as we press any key, that message is returned to the plug board where the after being sent to the plug board, as we had seen just in a while, we are showing you again for ease of clarity. As soon as you press any button, it first goes to the plug board where it may not be exchanged. So what exactly is happening in the plug board is that, let's say I have A and I have B. So instead of actually explaining you the plug board directly, what I'm going to do is that I'll explain you plug board and rotor together because the wiring in them is somewhat similar, only there's a short difference between that, and I will tell you later on. So let's say I press a letter Q. So after pressing a letter Q in the key switches part, it is going to take it as input, go to the plug board, and something happens out there. For now, let that be some operation X. So operation X happens over Q, and then the current flows, and that current goes to the rotors. And in every rotor, if you can notice out here, there is some switch occurring, right? Similar switch occurs or similar operation X occurs in the plug board as well. Then the current goes to the reflector and some other letter is returned. Okay, so this is exactly how the current is flowing and we are getting the output. Let's see how exactly the circuit is made as well. So this is our circuit. So what exactly was our operation X or how the letters were getting switched? This is how exactly it is. Let's say I press A. So this is the key switch. So the A is connected to C. So I get output as C. So this doesn't show the total working, how the plug board, rotor, and then again plug board works, but it individually shows how the plug board or one singular rotor works. So whenever there is some input, it gets changed to some another letter. And that's what we have to first imitate in our coding using C++, obviously. And first we imitate this, and this is basically what is happening in the plug board. We are just switching off the letters, but it is important to remember that the plug board is static. What exactly does it mean is that once you have entered the plug board settings in our C++ code, you can't change it. However, the rotor itself is static, but because of its settings, every time you press a key, the rotor keeps on shifting or turning. That is why every time a new letter is generated for even the same input. Like if I press Q for 1,000 times, I'm going to get. Okay, let me not tell you if it can give different outputs all 1,000 times or no. But let's say for now that it gives different outputs. Let's assume. So it gives the different output for all 1,000 times for the same input. So basically all those rotors are turning. So the first rotor turns for every time you type. I press Q, it turns once. But the second rotor turns for every 26 times. That means when the first rotor has turned for a total of 26 times, second rotor turns once. Similarly, the third rotor has similar dependence on the second rotor. If the second rotor repeats for 26 times, then the third rotor rotates once. So on till the sixth rotor. Here there are 3, in my model there are 6. Mine is obviously more advanced than Enigma. So there is our bot. Okay, he understood something. I guess you also understood. If at all you didn't, just go back to the video and you can look back at the circuit, what exactly was happening in the Enigma, and look at my description. Then, so let actually look at the maths behind our project, because to actually know why it was important then and why it holds significance now is why we are going to build it on remove some of its flaws, which we will be discussing later. So what exactly is the math and why is it significant? Is that first of all, how many combinations do you think are possible by Enigma? So 158 million, 158 billion, 158 trillion, or US GDP, obviously, like my favorite answer, US GDP. Let's go. So let's leave that for now. Let's calculate it mathematically. If at all you want to, just go back to the video, pause it, and you can try to calculate yourself. Since we saw that rotors can turn every 26 times for the first 26, second 26, third 26, so there are total 26 cube, or basically 17576 outputs what you can get. And apart from that, there's one more thing. You saw the plug boards, right? When I said they were manual, are you underestimating them? That oh, this is static, this can't be changed. But the person who is setting them, he can obviously change them, right? Like for today, I'm setting for some combination. Tomorrow it is something else. So how many are those possible? This is the combinated formula which I have written. 26cn into 26 factorial, so on, so on. And basically what this 26cn doing is that we are choosing the number of letters which are going to be not paired, and so on the combinatrix is happening. You can search it out, or you can even try to understand it by parts, taking 26cn separately and 26 factorial and this part separately. 26 factorial by this part is basically giving us the number of possible groups of 2 which can be made out of remaining number of unpaired letters. And this value gives maximum at 6. So if at all you remember, I had said that we are going to pair 10 letters with another 10. So do you understand why exactly n is equal to 6 now? Because when n is equal to 6, that means that 6 letters won't be paired, and this thing will be giving the maximum number of combinations possible. That means when 10 letters are paired to another 10, we are going to get maximum number of combinations. But what exactly is it? Is it more than 158 billion, or let's say US GDP? Let's see. So it gives total of 158 quintillion combinations, which was back then, the old Enigma or the oldie. Let's see what are its flaws so that we can actually overcome them. So no letter could be encrypted to itself. So first of all, in my explanation, I didn't give you a lot of information about reflector, and the sole reason is that I didn't actually wanted to reveal you the flaws in it. So when you see why A can't be encrypted to A, let's say I put A, and let's assume the output is A. Since I said the order of input goes as plug board, rotor, and then again plug board. So let's say plug board shifts A to H, and here since the output is A, that means the step just before the plug board, the output should be H. That means when I'm giving the input as H, the output should be H from the rotors. However, since the reflector is present and the reflector always changes the letter to something else, it is just not possible to get both input and output as same in Enigma. using this flaw, the those who were trying to decrypt it, it made it just very easy for them to eliminate options, and also made some machines as well. Humans are just not possible for this. And rotor wiring was static. So I said that the rotor wiring, and even if you had seen the video which I had just now showed, the rotor wiring was static. However, the rotors were rotating. So let's say I give a little bit of bribe and get the machine from someone, then I know what exactly is happening in the rotor, right? That was then if you know, then you have to only work on the plug board combinations, and once you're done with it, you have the decrypted message with you. So those two were the very big flaws. So rotor wiring is something which probably we have to use modern encryption techniques like RSA or some other techniques. But we can change or actually modify the first thing, or the no letter could encrypt itself. So we can actually make something so that it can be encrypted to itself. So what exactly can we do? So we are going to eliminate the reflector. And that's what I'm going to share with you. I have eliminated the reflector instead of three. Since it was passing through three, then again coming back to the three rotors before going to the plug board, I have kept six rotors. So that is how exactly I have exchanged the three rotor instead of six. Six rotors instead of three, sorry. And eliminated the symmetric working. So symmetric working of the program. As you saw, the rotors, it went in, let's say H was going in the rotor, then we are getting Y. Similarly, if Y went in the rotor, H will be coming back because it's basically forming an electrical circuit. You pass input from either of the sides, so you're going to get output from all the opposite side, and you know that. So it used to work symmetric in the oldie or the old Enigma machine. But what is happening in my Enigma or the Enigma E enhanced model is not going to be symmetric. So it will be having some issues in the decrypting, but I've solved it out and I will be explaining it how exactly I've done that. And even without the ring settings, like what exactly are ring settings, you can change the internal wirings of the rotors as well. This was not present in the old Enigma, but there were modifications done in the old time and it was possible in some of the machines. So even without using the ring settings, which actually gives a considerably high number, I'm able to get 300 times more than that of Enigma. Let's see forward what exactly I have done and some of the methods which I have used. First of all, there are two things which we are going to focus. First one being the user settings. Second one being the encryption and decryption part. So what exactly is up in the user settings? So we are going to set up the plug board. So remember, we had studied about the plug board and rotors. Those two are really the most important parts. And just remember, so plug board, rotor, plug board. This is how the encryption and decryption flow is going to be there. So first of all, we have to set up the rotor and the plug board as well. Then when it comes to the interesting part, that is the encryption and decryption, we have the plug board shift, rotor code for encryption and rotor code for decryption. Why exactly are those two different? Because if you look at the old Enigma, the rotor code for, basically there was no code, but the working of encryption and decryption was same because it was symmetric as just discussed before. Since it is not symmetric, there are two different codes. Let's actually look at the user settings first, how we are going to set up our rotor and plug board. But before that, this part is something which I would recommend you that if at all you know, you can skip this part, go to the forward part and enjoy what exactly is happening in the machine, which I have explained in a pretty clear manner and a crisp manner as well. So we have the library IO stream on board with us. Basically, it is for the output and input, which is going to be the C out and C in. But we are not going to use scene because of some issues that I will be discussing. And string object which you are using from standard, which is standard, and this is scope resolution operator standard string is going to be very important. And complementary to the iOS stream standard, we are going to use using namespace. So namespace is nothing but like it is to give name to a bunch of code or let's say a lot of variables and codes introduced in it. And identifiers are the name of objects which might be variables or function names inside the namespace. So arrays are the MVPs obviously, but after string because string is going to be used everywhere. Arrays and string objects using them as char vectors. So how I'm going to use them as char vectors, how am I going to update them? I'll be discussing that later. But just for now, briefing about what are char vectors. Basically, they are dynamic and what they are storing are characters. And getLine. getLine is something which we are going to use as substitute to stream. And that's why are we using getLine? is because get line is going to take input even if I mention spaces or anything. And if at all I don't want to mention take input after the spaces, there's something called as delimiter. So input stream is going to be cin. Where to store is basically the variable, which is going to be a string variable, of course. And delimiter are basically there are single character inputs after which it won't be taking input. Suppose I mentioned a space, that means it won't take input after the space. If at all I don't mention anything, then by default the delimiter is set to the new line. Basically, whenever you press enter, when you go to the new line, it would stop taking input from that. So the initial part will be taken as input, and after that if you type anything, then it won't be taking any input. Let's quickly go forward to the plug board and rotor settings then. So this is how I'm introducing the plug board, which is going to be a 2D array to 10. So this mentions the row, basically this, which is let's say y-axis, and 10 mentions the x-axis. So one part of the plug board combination is going to be along the first row, and second one will be the along the second row, and everything will be paired. I will be showing you how exactly the code is working as well, and that is going to be a little bit long. So for that, I will recommend you to use a laptop, because on a small display the code might not be very visible. So preferably use a laptop, and let's quickly see how exactly am I going to enter the plug board settings. In the plug board settings, we have our first for loop, which is for taking 10 inputs from the user. As I mentioned, there are going to be 10 pairs, right? 10 pairs of 2 each, obviously. So let's say Q is paired with W, E is paired with R, so on. So if Q is paired with W, now I'm going to take 2 inputs, Q, W, then E, then R. So all of those are going to be stored in our array. And since it is a 2 into 10 array, so since it has 2 rows, so Q will be in the first row, like the first column, and W will be in the first column but in the second row. So you can imagine it, right? Or else it is sort of obvious. So let's go forward and let's look at the second step. Then we have the while loop. Why is the while loop important? Is because in the old Enigma, the user couldn't actually play with it. But if the user is trying to play with our machine right now, let's say he or she inputs some special character or number, then it becomes a really big issue, because we are supposed to change or encrypt letters and not special characters. So we will be checking using the while loop, which will be running again and again until the user provides us with valid inputs. Before we go into the if part and the again any loops which are present inside, I will explain you what are valid inputs and what are not. So for now, the valid inputs will be those. First of all, Q can't be paired with Q because we are pairing, so we want different letters, obviously. And if Q is paired with W, that necessarily means that those 2 letters can't be paired with any other letters forward. What do you mean exactly? So basically, Q once paired with W, Q can't be paired again with U, or W can't be paired with I or something like that. We need to be careful about that. That is why we have the first if-else pair, to check if the 2 characters are distinct and if they are single letters or no. That is why I mentioned in L1.length is equal to 1 and L2.length is equal to 1, and put an and between them, so that even only if when both are true, only then the code will run. And here also I have checked that L1 is not equal to L2, just I had mentioned you. And here I'm checking if they are letters or no. So what exactly is that? So this is called as typecasting. So when I have mentioned int in the circular bracket sort of, and then L1.0, that means the 0th position or the first element of the string, which is the first character. And since the length is also checked to 1, so when the first character is less than 91 in the ASCII code, since I am typecasting it to integer, and greater than 64. Necessarily, if you go to the ASCII code, you can just Google it out. ASCII code from 65 to 90 actually refer to the uppercase letters. And that is why I'm checking it, whether it is an uppercase letter or no. And once it is, then we take the input, and there is one if condition where I is greater than 0. Why exactly did I need to mention I is greater than 0? Let me leave it for now and go to the next part. For now, I will be explaining it obviously, and I want to show you here why exactly I have used. So let's look at the for loop. So if you look at the for loop, we are going from j is equals to 0 to j is equals to I. Basically, what we are going to try is that we have a 2 into 10 matrix. In the 2 into 10 matrix, I'm checking for each inputs before the actual input which I'm providing now. If the letters are repeated, you remember I had said Q can't be paired with two letters together, or even separately. Q can't be paired with W, Q can't be paired with U, both at the same time. So here we are checking if the letters which are inputted now are not repeated anytime before. And since the check can't be done for the first input, that is exactly why there is if I greater than 0 present here. So let's go forward. So the second if else just I said you why exactly is it present is to check whether it is the first input or no. And if at all it is the first input, it is not the first input, then we go backwards and look that are the letters repeating or is that a valid input or no. Let's look forward for the rotor introduction and rotor settings. So first of all, before showing the actual part of the code, which is pretty brief and static for the 3D array, but a 1D array is going to be dynamic. So 3D array for saving 6 rotors. So this is going to be a bit complex and you have to extend your idea from plugboard to rotors. So suppose you have a 2 into 26 matrix, but there are 26 layers. That means there is a 2 into 26 matrix here. Behind that there is one more, one more, so on until there are 6 matrices like this. And obviously, in the 2 into 26 matrix, the first matrix or the first row will be saying us about the input, the second row will be telling us about the output. And after that, we are going to go to the second row and so on. We are going to take the inputs. No, actually, this is going to be static, but 1D array, we are going to take the inputs. So, how exactly is the 3D array looking like? This is how it looks. 6, the depth, 2 is the number of rows, 26 is the number of columns, just as I had mentioned. And each thing has its significance, right? 6 is for different rotors, 2 is for input and output rows, and 26 are the letters, and the letters to which it is encrypted to. What exactly is 1D array doing? Do you remember I had said the rotor is rotating and the rotor will be shifting its position. That means if A is getting changed to C, the next time I'm pressing A, it will be going to change to I plus 1. Or let's say after C, the next input encryption was D or Z. So it will be changing to Z instead of C. And every time you type, the first rotor will be shifting. The shift in the rotor will be stored in the rotor S array. And since here, since string rotor is not very clear, I will be showing you that as well. Just a second. This is the video where I'm showing you the how exactly is it looking. So as you can see, this is our first row where A, B, C, D till Z. So this is our first row. Then here is the second row of the first layer. We are looking at the first layer now. So be careful. And as you can see here, there are some random letters. So why exactly is it random? We may take the input in a structured way, but since we want to encrypt it, the output has to be somewhat random. That is why I have kept there some random letters which is going to change to. We are going to say how exactly it is going to change in the coming part. So let's just go forward and look how exactly both of the things like plugboard and rotor is working. The rotor settings. Since I want 6 inputs for the rotor shifts or how much it is going to change. And the rotor shift is going to be dynamic. That means every time I'm going to input a letter, the next time it is going to be something different. Why is it necessary? Basically, the Enigma uses the same method. Every time you press a letter, the rotor turns. So that the next time you press something else, it follows a new path of electric circuit. And basically, we are going to replicate it apart from removing its flaws, obviously. We are just perfect. So here, we take in the rotors, and if you have understood the plugboard part, I don't think I should explain this much, but you can take a look and zoom through the screen to look at the code. I'm taking the input, I'm taking 6 inputs, checking it if it is valid or no by while loop, by a boolean which I've defined as check is equals to 1 initially. Until it is checked, I have to keep on checking and setting it to 0 out here after a series of if and else, which we'll be discussing in a brief time. So this is the first for loop, then there is a while loop to check, then there is a if else pair. If first we check if it is a non-null entry or no. And why exactly am I checking if it is a non-null entry or no? Is because again the user might by mistake press enter if it is trying to enter the entries too fast. So first we check if it is a non-null entry or no, and if at all it is not. Good thing to say. We then check if it is an integer or no. Again, if the user is somewhat you know whom I'm talking about. He's trying to play with our code. Then he might press some letter, and then he might get something random sort of. then we don't want him to fall into a trap. We want our code to be just as perfect as any other code. So we check if it is an integer or no by again looking at the ASCII values. So in the plugboard part, we had checked if it is a letter or no. Here we check if it is a number or no by going into the ASCII part by typecasting it to int. So I go to the number by taking a look at going at n in bracket I and typecasting it to ASCII value using int. So you can look at the format out here, and if it follows both of the conditions that it is a number which is less than 57 and greater than 48. Here I'm looking if it is not, so that I can tell the user that you are just not entering a number, please enter again. So we keep on checking this, and if at all it is an integer, we check for all of the like let's say he puts the input as 1 2 3 4 5 7 8 some number, but at the end the rotor shift is going to be modulo 26. Why? Because let's say I rotate a rotor once, twice, thrice. All those things are going to be similar. But once I rotate a rotor 26 times, it's basically going to be present in its original position. That is why I've taken modulo 26. So if the int check is 1, that means after going to every part of the integer, which is initially a string, which I am going to change it to an integer by stoi or string to integer function is provided by the iostream library, standard stoi. I'm changing it to a integer once I've checked that all parts of the string or the characters are referring to an integer or no. If once it is, then I set it to the number and check is equal to 0. That means I successfully checked. Now we can go to the next input or the next rotor settings. So on keeps on repeating by the for loop until we get 6 entries, and then starts the encryption part. Let's quickly go through it and look what exactly is happening in the encryption. First, plugboard shift. Though the entry part of the plugboard is somewhat lengthy because you have to mention Q, W, 10 entries like this, it is sort of bulky. But once that is done, the plugboard shift is very simple. And I'm going to explain you very clearly. For int I is equal to 0, so on. So again, we are scaling through the string, whatever input there is. And if you have mentioned, I have always used references. Why exactly I'm using references is, I will tell you. But if I'm using references, when I'm going from I is equal to 0 till int dot length minus 1, as I mentioned in the for loops constraint, that means I'm going to every part of the string. From here, if you can see in I, that means I'm going to every part of the string. Then, as per every part, I'm going to change it accordingly from the plugboard. So PBC, if you remember, in the plugboard settings part, I had said you PBC is basically a 2 into 10 array, where I'm mentioning the input and output, or the reverse order as well, the pairs of the letters which I'm going to pair up. So I shift it accordingly. First we go take every part of the string. The second for loop is for going to every part of the 2 into 10 matrix. We'll look at the first part of the matrix, which is the first column, second column, third column till the 10th column. Once we look at all of the columns, we check if either the first row or second row element of the first column is equals to the letter. If at all it is, we just shift it to the other variable. If you can see here, you can see that from 0 to I, this is how I'm shifting it. And why exactly I mentioned a 0 out here is because the original inputs in the PBC are in the form string. However, when I'm looking at in I, that means the string variables individual characters. And since they are characters, because I'm treating the string as a char vector, I have to change the string to a character. So I'm taking the 0th part or the 0th index element, which will be a character because PBC is a single letter input, because we had put suitable constraints over it. And if at all you missed the part, you can just take a quick recap and go back in the video. After the second while loop is done, we check it out, we switch the letters, and then there's something interesting coming out for you. And that is the rotor encryption. The rotor decryption is not exactly similar, but we'll be taking a quick run through in it, and I'll be explaining that part as well. So here, in the rotor encryption, we can see that from I is equal to 0 dot in that length, we are going to go from I plus plus so on. So again, what exactly am I doing here is similar to the just a second. Is similar to the plugboard working, how exactly we were doing. So in the plugboard, just as how we were taking each parts of our input string, and as you can see, we were taking each part of our input string, and then we were checking for all of the columns of the Do you remember the plug board shift which I had mentioned before? That this letter is going to be paired with this and we'll be shifting them accordingly. That is done by the if else pair anyway. The similar thing we have to now do is with the rotor encrypt part. So with I is equals to 0 till index length, we are scaling through the string. Second part is to scale through the layers. Since the plug board was a 2 into 10 matrix, so I have to scale it once. But since here our rotor is a 3D array or a 3D matrix sort of, we have to scale it twice. Once we'll go into the layers. Let's say I go to the first layer once because you can select any order, but how I have selected the first layer, second layer, so on, is so that there's ease of decryption as well. The order won't change the amount of how difficult or how hard it is, but yes. So from 0th layer to the 0th index to the 5th index, that means the first layer, second layer, third layer, till the 6th layer, yes. We go from the first layer to the 6th layer. Then after going to from first layer to 6th layer, as I mentioned, second layer, about the second for loop, the third for loop, what it does is that it goes from all of the columns. So the first for loop is looking for all the inputs in the string, each character. Then we'll look at our rotor array, which is individual layers. So we look at the first layer. Then in the first layer, the second for loop helps us to look at the individual columns, which are 26 columns as we had defined before. So we look at the individual columns, 26 columns, and look if our element, which we had mentioned in the string, is equal to the individual input in the rotor array. If at all it is so, then we are going to change it with corresponding output. If the first row was mentioning the input, we had mentioned the output in the second row. And that is why if rotor J0K, which is the input or the input array, first row, we are going to change it with the output, which is J1, because 1 is the second row, 0th index represents the first row. So the second row and key plus rotor Sj. So this mentions that the amount of shift what we are doing. K will be just mentioning the index, but rotor, when we add rotor Sj and take a modulo 26, so it mentions how much the rotor has to be shifted. So A won't be going to C directly. It might get to Z, but something else might be paired to Z in the initial thing, right? That is what we are going to use here. Since A was going to C and something else was going to Z, let's say Q was going to Z. So we add the initial shift, which is mentioned by rotor Sj, which changes A input to which is equivalent to Q, and then it is shifted to Z accordingly. And then we set updated is equals to 1. Once we will find the right input. And to make the thing dynamic, we are every time our encryption for singular part of the string is successful, we are mentioning this thing. This changes the rotor settings accordingly, or the rotor shift as we had done before. The first rotor, as I mentioned in Enigma, turned every time. Second rotor run once in every 26 times. So this is what the second part is doing. Third part is doing for every 576 times or every 26 times the second rotor runs. That means every 576 times the first rotor runs. But how do we count exactly how many times the rotor is running? For that, we count on the string length, which is given by I. I plus 1 gives us the number of strings which we have gone through and how many times we have changed. That many times the rotor keeps on turning, and that is counted. So every 26 times, 576 times, and into 26, so on till the sixth rotor. And what is this question mark and this colon out here? Those are called as the ternary operators. So if the condition out here is true, that means let's say if I'm looking at the second rotor, or I plus 1 modulo 26 is equal to 0. So if at all it is equal to 0, that means our rotor has turned 26 times. So if at all it is true, then we update it plus 1. And why again modulo 26? Because we have to maintain the constraint to 26 only, or less than 26, from 0 to 25. Because if at all it is rotating more, it is just representing any number from 0 to 25. It's just equivalent to that. And if it has not rotated till 26, then we are setting it to 0. There is no increment. And if condition, so on. And if at all we do this exactly in the reverse order, we are going to get the decrypting model. So I have not exactly mentioned the decrypting model in the PPT because it's going to make the PPT bulky. I will be showing you here itself. Since here we are going from the first layer to the sixth layer, what we are going to do in the decryption part is that we are going to go from the sixth layer to the first layer. We go to the sixth layer, put it as the input. But here, when we are looking at the going through the columns, we don't go at the first row. We check it with the second row. If it is equal to the second row, then we go to the first row. So are you seeing it now? We went to the first row to sixth row in the input or the encryption part. So we go from the sixth row, sixth layer to the first layer in the decryption part. And since we went from the first row to the second row in the encryption part, we are going from the second row to the first row in the decryption part, which is mentioned out here. Once we have done the changes mentioned accordingly, the message will be decrypted as well. We will be taking a quick run through about this as well. But first, you might have mentioned or seen the standard part in the settings part of the router and the plug board. So what exactly the standard was doing is that, suppose I mentioned Q in lowercase, W in uppercase, ER in lowercase, T in capital or uppercase. So all those things are somewhat ambiguous. But how do we take all those things as inputs in our plug board? Or let's look at our rotors. So we want it as something good or decent looking, right? So to change it into something decently good or something good looking, we are using the standardizer, which changes each alphabet to its uppercase character value. So we first scale through the string, obviously, or scale through the input. We'll take a look at the input, then we scale through it. We take in the fundamental character parts of the string. After taking the character parts, then we check if after typecasting it, if the ASCII value is less than 123 and greater than 96. Basically, if it is a lowercase letter or no. If at all it is a lowercase letter, then we just subtract 32 from it, and that gives us a capital letter present in it. So this is how the first for loop is for scaling. The second if is for lowercase to uppercase by adding by subtracting the 32, and then we again typecast it to character by char present here and store it back in the input. And here is why references are important, because I didn't want to create too many variables out here and add some unnecessary conditions. Suppose the input, which can obviously be a special character as well. Now that doesn't need to be changed, right? But what if I don't mention in here? That means it won't be processing our special character and giving some output to us. Or if at all we want, we have to add one more else part, that if at all it is not a letter, then it has to do so and so part. But to not do that and to reduce the lines of code and also the number of variables which we have to introduce, I've used references. So that there's just no need to change the special characters or any already present uppercase characters. It will change only the lowercase characters. And this is the code. You can get the code out here, but since it might not be very convenient for you, so I'm going to show you a quick run through the code. This is our code. We have discussed most of the parts, such as we have discussed the string PBC or the plug board combination out here, then the string of rotors, this array out here, and we also discussed the rotor shift. So the rotor shift is dynamic. The plug board combinations are dynamic. However, the rotor array in itself, the shifts I have already mentioned them. Like this is the first row, second row in the first layer, and so on. This is the standard. We have discussed this, how it changes the lowercase letter to uppercase. And yes, plug board, enter the plug board settings, set up rotor. We have discussed all of those parts. The one part which we had not discussed was the rotor decrypt. So I'm going to give a quick run through this. As what exactly we do in this part is that we go again, we scale through the input by going from the first character part of the string to the last character part. We are going from the 0th element to the in.length -1 element in the string. And once that is done, what we do is that we again go through the rotor. Just as we go through the rotor from the last layer to the first layer, which is j is equals to 5 to j is equals to 0 index, we go from the last layer. After we are in the last layer, let's say in the last layer, we check if in each individual column the output is equals to what is our input. Because since we are going in the reverse direction, if we won't be checking the first column, we will be checking second column, because that's what from where the output came for the encryption part. So you have to go in the reverse order to get the output. So we go to the second column or second row, and then we go to the first row. We check with the second row, which is mentioned here, that if the fundamental unit of the string, which is character, is equals to rotor's first row element of the kth column, If at all it is true and we have not updated it already, we will be going to update it to this first row element of the k minus rotor sj, because every time we are doing so we are mentioning a shift, right? So that shift is also to be included here, and there is some ternary operators included here. And what is the need of them exactly is because when we are adding, so initially when we were adding there was no issue because we are taking a modulo, but now since we have to go in the reverse direction, we have to subtract, keep on subtracting so that we actually get through the rotor shifts. So rotor shifts for the forward array. For doing so, we have done k minus rotor sj. And if at all it is negative, because this thing can be negative, it is negative, then we just add a 26 to it. Because the modulo value won't be changing, but it will be changing the remainder from negative to positive. And if at all it is not, then it's perfectly fine for us. We change it to update it equals to 1 and we have got it. So int main part basically defines the main or code part where we'll be calling all the functions, because since this is a modular function code, so we'll be calling the get line part. Here we are taking the input from the user. Then we are standardizing it, basically changing it lowercase to uppercase, enter plug board, setup rotors, which is common in encrypt part and decrypt part as well, as you can see here. Once that is done, plug board shift, rotor encrypt, rotor, and then again we have a plug board shift. Since there is certain symmetry, even though the encryption decryption part is not symmetric, since we have to go from the opposite number of layers, like first layer to last layer to first layer, first row to second row to the first row, respectively in encryption and decryption. But since there is plugboard shift and plugboard shift which are similar involved, we have also plugboard shift out here and plugboard shift out here after the decryption is done by the rotors. So once the rotor is encrypted in a message, as we just discussed, it goes to each column of each layer and changes accordingly. Similarly, when it is done by the decryption part of the part, then we pass the input back to the plugboard shift. And since we are using references, there's no need to create any extra variables and to consume our memory, because our code is already very bulky and it seriously needs a lot of memory in reserve as well. After once that is done, we are using the destandardizer. So this thing, I have not introduced you to this before, but what exactly is it doing is that just how standardizer work, it is working in exactly opposite. If at all we have anything in uppercase, I'm changing it to the lowercase, because to look at those capital letters is just not friendly, or apart from the titles of movies or something very formal. So make it user friendly, I'm changing it to the lowercase, and then we give the decrypted message. And if at all the user is not entering E or D, that means encryption or decryption mode, we are telling him that he is entering some invalid mode of operation. Come on, now let's get into some interesting part and let's see how exactly our code is running. So just a minute. The destandardizer part. Okay. Just a second, everyone. There's some issue which is showing up, and as we have coders, we need to look through it as well. So on. It seems it is correct. Just run it again. So it's running. It was just a false error. Sometimes it might happen because our program is bulky, right? So let's encrypt the message. So what you might like to encrypt? My code is best? Sure, let's encrypt it. Again, now the first part was the plugboard settings. We set the plugboard, then the rotor settings, then there will be the part which will be done by the machine itself, which is plugboard shift, rotor shift, plugboard shift, and then we'll be getting the encrypted message. First things first, let's go to the plugboard shift part, which is, let's say for ease of typing, I'm entering as Q, W. You can put it the input as anything what you wish, but for the ease of typing and quickly timing it up, I'm putting it as it is mentioned in the keyboard. And once we have entered all the valid pairs, here we are going to enter the rotor shift, or how much the rotor will be turning each time, or the initial shift basically. So the first rotor shift, let's say it is 8, then 0, then 7, then 3, then 1, then another 8. So our encrypted message is this. Isn't it cool? At least it looks cool to me. Let's copy it up. Now I have copied it, and now let's look exactly how the decryption part of it is working, because both are really significant part of our code. So in the decryption part, let's go to the decryption mode by pressing D. We paste the input which we want to decrypt. Then again, the rotor settings. Now, if at all I try to enter some random input, let's say I enter some wrong pairings, like Q is paired with E, W is paired with W, R, T, Y, U, I, O, P, A, S, D, F, G, H, J, K, L, Z. And the rotor shifts, even if I assume the rotor shifts are correct, which were initially 8, 0, 7, 3, 1, 8. So we are going to get the wrong decrypted message, as you can see. Why exactly is this? Is because we had mentioned the wrong plug board settings. So our code won't be decrypted the same way how it was done in the encryption part. To get the same input, we need to know all the plug board settings and the rotor settings properly. That is how encryption method works. Only the user and the another user who is encrypting or decrypting it knows the keys or the plug board settings and the rotor settings. This is how it works. Let's paste it again and enter the right settings this time to get the decrypted message here. See, you see here, I purposefully mentioned the empty character out here and it said enter valid entry pair. That is how we are checking if it is actually a letter which paired with something else or no. Let's enter something valid now. Shift 1. So let's put the initial shifts 8, 0, 7, 3, 1, 8. Okay, we went in encryption mode. Sorry. We have to go to the decryption mode. I just forgot with the flow as I was talking with you guys. So let's go to the decryption mode, put it quickly. Q, W, E, R, T, Y, U, I, O, P, A, S, D, F, so on. Oh no, we have mentioned the wrong shift again. No, no, I'm messing it up. Again? Oh no, it's sort of getting clumsy now. That is one thing which I feel is the something which we can be probably improving over it. And you can tell in the comments what exactly do you think can be done about my code and how exactly can it be made little more less clumsy and user friendly. Because rotor settings and plugboard settings are essential part, and how exactly am I going to replace it is sort of challenging. So you can see the decryption part has successfully decrypted our part. And if at all you are trying to mess up with the code, or if at all it is some foreigner who is trying to intrude in our code and getting to the decrypted message, he just can't get through it. If at all he is using the wrong plugboard settings or the wrong rotor settings. Only when those plugboard settings and rotor settings are correct, it is going to give you the same output, and we have discussed the logic. Let's end the presentation here. And yes, you can obviously get the code here and try it out. Just paste the CPP file in any C++ compiler or go to VS Code, which is obviously the best, and try it out by yourself. Till that, bye bye. Wait, we have someone else with us as well. Who exactly is it? Oh, this guy. He's just some foreigner trying to break our code, but with manually rotating the guys. I understand your pain. Chalo, bye. Bye everyone. Let's meet at some other